Hi, welcome to number 4 in the expert series, and again we are slaying some C++ myths. If you haven't seen video number 2 in the series, have a look. This starts very much the same way, with a quote from the inventor of the language himself, and we're going to look today again at efficiency and the myth that for efficiency you must write low-level code. We're also going to cover the myth of code bloat and look at large complicated programs only. First, why am I making this? There's a number of reasons. I see a lot of holy wars on social media where people swearing that C is better for everything, especially in embedded systems. In my own FB groups, I see many discussions, and I hear, quite frankly, a lot of nonsense and a lot of uninformed nonsense and a lot of confusing nonsense. And given that my groups are set up to help beginners, it kind of bothers me that people that should know better put out information that is just factually incorrect. And yes, I'm on a mission to correct misconceptions, convert people to C++, and generally make the world a better place. So what started this one? Well, this piece of code. As a little bit of background, this is not some kind of academic exercise. This is a real-world example. I would say converting, but it's actually a ground-up rewrite of some libraries on ESP8266, ESP32, which have been causing me a lot of problems for a long time, and not just me, anybody that uses them, because they're fundamentally flawed. And they're so flawed that they have to be totally written from the beginning. So this is from the real world. This function here is called generate event message. When I first saw it, I looked at it and thought, what on earth is that meant to be doing? Now, I can't expect you to read the code at that level on the screen, so let's zoom in a touch. There's a lot of things going on there, and I looked at it and I just really couldn't understand why it was so complicated and so involved, and why it was full of things like this. So I mean, this is, you know, what I call hardcore C, and the irony is I actually knew what it should be doing. So the function and purpose of that code was completely known to me, but looking at the code gave me no idea as to how it achieved what I thought was quite a simple end, and why it was so unnecessarily complex. And as part of my rewriting process, I thought, well, that has to be replaced, because I know that in C++ it's going to be a lot less lines. Now, this is what that code is doing. This is taken from the Mozilla Developer Network site. It's part of a web server that sends server-sent event messages, SSE messages. And what it's doing is this. It's taking an event, some data, an ID, and a retry field, and it is formatting them into a text string that is required by the SSE spec. And it's fairly simple, as you can see. If you've got an event, you put an event tag in. If you've got an ID, you put an ID tag. If you've got a retry, you put a retry tag. And the only field that's mandatory is the data, and you put in a data tag with the tiny wrinkle that if the data contains line breaks, then you need to repeat the data tag for each one. So that to me is a fairly simple process, and nothing that requires 77 lines of eye-boggling spaghetti. And that's why when I replaced it with C++, that was what I ended up running with. Now, before you all throw your hands up in horror, you'll note that I haven't included the retry value. One of the reasons for that is because it's not necessary. It only ever needs to get sent once for the connection to tell the browser what the timeout value is. So including it as a parameter on every message that you send is wasteful, illogical, and in my view, just plain wrong. So the code that actually lives in my replacement library is what you're looking at, which is 9 lines, including a tiny little sub-message function which does nothing more than concatenate the type, the colon separator, the content of the tag, and a new line. And really, that is all there is to it. Now, when you look at that and remind yourself of what it's doing, it becomes quite obvious, doesn't it? If there is an ID, add on a sub-message consisting of the ID and its string representation of the integer value. I'll talk about that more in a second. If an event has been provided, add on a sub-message for the event. Here's the expressiveness of C++. Split the data up into separate lines, and for each of those lines insert a sub-data tag. Now that's what that spec says, isn't it? That code, to me, one look at it tells me what it does. Now immediately I can hear the cries of horror saying, oh, that's more than 9 lines because you've got these other sub functions. Well, there's one of them. It's 1 line that's included in the count. So the only things that go against my argument for 9 lines are the string from int and the split. Now both of those are routines that I have in what I call my toolbox, and they're used in many other places in the code. So the actual overhead, it only comes from 9 lines because those are multiple reuse. However, when we get to the proper testing, I have taken that into account and factored them out, and you'll see that on the next slide. Because here is the code that my test program for this video is going to run. So what you can see there that I've done is, first of all, I have added back in the reconnect to make it a fair example. So this is where I've basically manually inlined the sub-message thing. And also what I've done is I've removed the dependency on string to int by using I2A. Tiny bit of history. I wrote string to int years ago when ESP8266 didn't include I2A in its core. On writing this code, I discovered that it did, so I've put that back in. So in between the 2 comment lines there, that is the code that the split function evaluates to using a fairly well-known C routine, strtoke. And that adds an extra, however many lines, not many. So that's what we're going to run with. So the absolute truth is that it's 15 lines of code. But in effect, it's only 9, because when you consider that this block here is refactored into many other places, the actual overhead is 0 in this real world example. And that's the whole point of this. This is actual code from actual libraries that are going to get deployed. So the rest of the code, just at the top, obviously we have some language specific declarations of the message and the event that we're going to send, and that's pretty much all there is to it. So the rest of that part of the code is the equivalent native data types for the SLOC77 example, which you've already seen. And then there's the timing code, which is very simple indeed. what we do is, first of all, we run using the appropriate language constructs for each type. We run a confirmation test to print out the results of generating a message with that data that's been provided, so that you can see in the results that the two pieces of code do exactly the same thing. Then we just take the time, we iterate 10,000, 100,000 times, I think, in this case, again using language specific versions of the relevant calls, and then we print the results. So there really doesn't get much more simple. The only tweak in there is that I have to feed the watchdog in that loop, because when you're doing 100,000 type calculations, the processor objects and it times out. But it's the same for both examples. Moving on then, let's look at code bloat first. Now then, here's the first nail in the coffin of people that will tell you that C++ is bloated. I tried two separate compilation optimizations, fast and S. As you can see, I can't argue that C++ is smaller, but I don't call 0.44% bloated. Neither, let me get rid of that, neither do I call 0.65% bloated. And in actual fact, just for fun, the heap space in the C++ example is actually smaller than it is in the other two examples. So let's not niggle about silly little differences like that, especially when you take into account the fact that the C code cannot be refactored. None of that middle guts of spaghetti eye boggle can be reused, and therefore that kind of philosophy propagates through the rest of the code. Ultimately, and I can tell you that this is true from my examples, is that the C++ code is smaller. However, in the example that we've got, those are the absolute facts. So, but the facts aren't just the whole story. Black and white code results aren't everything there is to know about programming, are there? So let's talk about reuse. We can't reuse parts of that complex code. My simple code relies on the fact that it reuses things that are already in elsewhere. The author of the SLOC 77 does things like hand rolling his linked list and string array, amounting to 194 lines, that make that first piece of code look clear and simple. I mean, it really is a rat's nest of pointers, and it is 100% unnecessary, because it's not even a one-line replacement in C++, because he still has to call his as well. So the call is the call. But if you call a standard library forward list, that is zero extra code overhead. So his approach is adding code. He is doing the code bloat. The C is the code bloat, because he's handwriting stuff that he doesn't need to write. Now, by becoming a hardline C person, when you're writing for the Arduino IDE environment, which is inherently and natively a C++ environment, which already calls many of the standard library functions in the lower level firmware, so your overhead is practically zero, hand rolling your own data structures is quite frankly an exercise in self-harm. And it's an invitation to bugs and code bloat. So there's the irony. In this particular example, the C code is the one that's doing the bloating. So the code that I'm replacing is larger, it's significantly more complex, it's much harder to maintain, and it's totally and utterly unnecessary. You can't refactor any of that spaghetti. But what we're really talking about now is the speed. So let's look at the speed comparison. So I think we've done in this example, I think we've done with the code bloat myth. It's rubbish, it's nonsense, it's factually incorrect, and people that propagate it should be ashamed of themselves. Let's look at the speed. There's the two runs side by side. First of all, there's the data test proving that they do exactly the same thing, and that is a fair comparison. The code is functionally 100% equivalent. The Arduino string and pure C code runs in 47,704 milliseconds to do 100,000 iterations. Now, I'm not going to tell you what the speed of the C++ 15-line replacement is, because it's quiz time. Pick a number. What do you think is the answer to the speed of the C++ version? Bearing in mind, you know, it's always slower, it's worse, it's bloated. If you're having difficulty, I'm going to give you a 50-50. So is it almost identical, or is it, wow, significantly faster? Well, no surprises for guessing that it's significantly faster. And I'm not talking a little bit, I'm talking significantly. I'm talking 3 times faster. Actually, just over. And for correctness and fullness, that was with the OS optimization. With the fast optimization, where the code difference is almost negligible size-wise, it is actually, ironically, with the fast compile option, the pure C does in fact run slightly faster, but it's 2.9 something or other, so it's not worth the argument. 3 times faster is what my code runs. So here's the summary then. Here are the facts instead of the hot air and nonsense that you hear on Facebook and in developer labs across the globe. We start with 77 lines of complex eye-boggling spaghetti, and we end up with 15, which is actually really only 9, lines of simple and expressive C. When you look at the code, it tells you what it does. You have the spec in one hand, the code in the other. You go, oh yeah, right, that's kind of obvious and simple, isn't it? And the code is 3 times faster. So I'm going to leave you with some final thoughts. As always, kids, beware who you listen to and where you get your information from, because in Facebook groups, a lot of it is rubbish. And I hope that the facts in this video have entertained and informed you. I hope you enjoyed the video, and we'll leave it there.